I wanted to do a video on LAB, CIE LAB color space, and I thought the best place to start was again from Photoshop. So this is an image. This image, as I shown in the last video, this is the composite. This is the lightness channel, in other words the lightness component of the color. This is the redness greenness component of the color, and this is the blueness yellowness of the color. LAB is, it grows on you. It takes time to get used to. I remember at the beginning when I was studying color management, at way back in 1996-97, when the hot item was Heidelberg, or at the time linotype, lino color. I remember the first time I came across these concepts was in the context of LCH, lightness chroma hue value. There could be, you see here, an additional choice option. Instead of just these 5, 6, there could be a seventh one called LCH, but the Photoshop engineers never wanted to do an LCH. Anyway, the lino color was pushing the LCH color space, which is a transform from LAB. But the beautiful thing is, what's easy to remember or to grasp is the lightness channel. The rest takes time to sinking, I agree, and but that's not an excuse to not take a look at the LAB readout in the info palette. So let me go over quickly this image to show a little bit about LAB in Photoshop. Over here we have a color checker image. That's the classic color checker image. This one was created digitally, but you can find it in real form by buying it online. It's about the size of an 8 by 11 sheet, and it's used extensively by all color management experts, I would say, but it's also used in color television and reproduction and many places. It's surprising, and it has very unique qualities. I'm not gonna go over each of these, but suffice to say that this at the bottom is a grayscale, as I'm sure you have quickly noticed. It goes from black, not complete black though, to white, and not complete white, because you see the readout, if I leave the color, the picker icon on the white, what appears as the whitest white, or what appears as white in this chart, the L readout, the lightness readout is 96. That's not 100. We know that the L scale, the lightness scale, goes from 0 to 100, and 100 is considered white, the whitest white possible. Imagine a piece of ceramic or some other white material that perfectly reflects all incoming light in all directions, and no specular components, all diffuse. Well, that's white. That's white for LAB. And here at the other end, it's not completely black. It's 20. The L value is 20, so that's lightness 20. So that's not completely black. If I was to select this area, let's say with this tool, let me select it. No, it's not a good tool for this kind of selection. Let me just retry my luck. If I was to fill this with black, see, if I go back to default values, and now if I press Alt and backspace on Windows, I get 000 readout in LAB. I can't point to it with my cursor because I'm going to lose the value over here. So the readout, see, that's very different from this color. this lightness. You see, this is not completely black. And same over here. If I erase, the difference is not extreme, but the difference is there. And the difference shows now that if I do this, there's no pixels at that point. All the pixel values are worth 100 and LEB. 100 and L, nothing in 0, nothing in A, nothing in B, because it's a neutral value. So let me go back here to what it was, 96. And let me undo this. So all these values in between the white, quote unquote, white and black, quote unquote, are these intermediate grays. And these corresponds to Munsell grays. You may have heard about the Munsell color system. If not, it's worth investigating, because it's a fantastic way to learn more about color and color management and colorimetry as well. So all these intermediate gray patches are, you see, 36 in L. This one is 50 in L, 52, 67, and this is 81. But the intent is to have 0 in A and 0 in B. So there is no redness or greenness component. As you can see here, the A and B is 0. Now what about the rest of these patches? Okay, let's go straight for the yellow patch. The yellow patch shows that it's quite a light color, because the L is close to 100. It's 82, so it's definitely in the same family as the white. And it's interesting that 82 over here certainly compares to 81 over here. If I was to select this image, this square, and move it right next to the yellow patch, do you think it would have the same appearance? It would certainly share the lightness appearance. I've selected some black pixels over here because of anti-aliasing, but you can see that these two patches, these two matches in lightness. It's interesting. You can do all kinds of experiment with this chart, by the way. Over here, as you recognize, the intent is to have blue, green, and red, and these are primary sort of additives, theory of color mixing, and this is subtractive color mixing, cyan, magenta, and yellow. And the cyan, by the way, over here is very nice. It you know, has an L value of 50. So if I go to this 50, for instance, let me try the same experiment, and let me turn off anti-aliasing at this time, and let me try to move this over here. And now if I can place them side by side, you should see that there is no difference in lightness. They appear the same relative darkness or whiteness, or if you want, or blackness, but they have the same gray, sort of gray value. If I over to the just select the lightness channel, you see there's barely a difference, because the difference comes from the fact that this is 52 in L and this is 50 in L. So they're very close to each other. The red is usually darker. That's the lighter, darker than 50. That's to have a red that is very saturated. That's the nature of reds. So you see there's here what's called an A component, positive A of 56. Remember, this is in a scale of 0 to 128 positive, and 0 to minus 128 negative. Next door, if I over to the green patch will show a minus A value, because it's on the, you know, on the green, closer to the green end of the greenness redness axis. So its value is closer to minus 128. Any value where the A and B is 0 is bound to be gray, is considered gray, and is visually should appear gray to our eyes. The blue, you see the blue here has a strong negative B value of minus 54. That's because that's the nature of blues, to have a strong negative B value. Let's see this blue over here. Not quite as strong, but it still remains in that direction, minus 43. and this value here minus 22. So you see, from minus 22 to minus 43, this is almost twice as blue. And minus 43 to minus 54, well, not quite twice, but it's still a lot bluer in terms of bluing, being saturated in blue. This purple, or this violet, but I think it's purple, as a blue value as well. How about magenta? Magenta has a blue value component because it's minus 13. This green has doesn't have a negative B value. It has a positive B value, so it has a yellow component, not a blue component. Over here, this B value is 68, and this B value was 57. So you see, if I look at the A channel, these should not be too far from each other. All right, I'm going to conclude this video because the time is running out, but I'll come back to LEB in more detail in other videos, because it's a inextinguishable subject. But just suffice to say that it's not it should not scare you. It's the heart of Photoshop. It's it has tremendous value to anything that you do, and I strongly recommend that you keep studying it. Learn how to interpret it visually, because it's going to be your friend.